Greetings, Math 10 students. Today we're going to be taking a look at sections 6.3 and 6.4 in the textbook, slope, intercept, and finding the equation of a line in slope-intercept form. This is an overview of the concepts in these sections. If you'd like to look at particular example problems, take a look at some of the other videos in this week's playlist. We're going to start with an example that's similar to some of the word problems that you'll see in Hawks, but gives a good overview of the slope, intercept, and why we might care about these things. On the left here, you'll see a graph that we've seen in previous videos. This is a graph of the college tuition and how it's changed over time. This is average college tuition for public institutions. And as you can see, way back in the 70s, people were only paying about $1,000, I think that's per semester, and that skyrocketed up to $12,000 and change in the 2009-2010 academic year. In this particular graph, the independent variable is the year, the school year, and the dependent variable is the average tuition in the United States that year. So independent variable, what we usually think of as X, dependent variable, what we usually think of as Y. And we'd like to use this graph, this data, to maybe make some educated guesses as to what tuition might be in the future. I have a 5-year-old girl and I'm kind of nervous about this. I want to know, hey, how much is tuition going to be when she's eligible to go to school? So I can take a couple data points from this graph, say, for instance, in the year 2010 and in the year 2005 for my two X values or independent variables. And if I look straight up, I'll see that the tuition in those 2 years was $9,706 and $12,467 respectfully. And if you look over at the Y values here, if you were to look straight to the left on this graph, you could see, oh yeah, that's around 10 grand in the 2004-2005 academic year. I've summarized this in the table over here. You see the X and Y value, the input and output for both of those years. I can use that data to figure out, well, how fast is tuition going up, relatively speaking, every year? So how much did tuition increase? Went from $9,706 to $12,467. Well, I can subtract those things and say, okay, it went up by a little over $2,000, actually a little under $3,000, $2,761. That was our increase. What I'm doing there is I'm subtracting those Y values. It's Y minus Y. That's going to come up again in another video, so a good thing to pay attention to here. How many years went by? That wasn't all over the course of 1 year. From 2005 to 2010, well, you probably don't need to do any arithmetic for this. You can know fairly intuitively that that's 5 years. But you could subtract two X values to figure that out. We've got X minus X. 2010 minus 2005 gives us 5 years that went by. So what was the rate of increase? How much did tuition increase every year? If it went up by $2,761 over 5 years, how much did it go up every year? Well, you would divide to find that rate. So to find the rate of tuition increase, I'm dividing the total that went up by over 5 years, and I'm dividing that by the 5 years. And I get an increase of about $552.20 per year. Wow! And this is for public schools. This is for publicly funded colleges and universities in this country. So that's quite a bit. Every year, on average, it was going up by $552.20. That's great. That increase, that rate of increase, is a rate of change, and there's a special name for this type of number when we're dealing with graphs, when we're dealing with equations that we're dealing with in this chapter. That rate of change is called the slope. It's how fast things are going up, or in some cases going down. How fast is your graph increasing or decreasing? That slope is a super important number because if I know how much college tuition is going up by every year, I can figure out how much it's going to be 10 years from now. If it's going up by $552 in 10 years, I can figure out, hey, how much is it going to be in 10 years? And that's actually the next thing we're going to do here. We're going to predict college tuition in 2020. Well, we need a baseline, so let's start with our 2010 number. In 2010, according to that graph, it was $12,467. Now I know it's going up by $552 per year. And as I was saying, in 10 years, if it's going up by $552 every year, after 10 years, I'm just going to multiply that by 10. My rate of increase, $552 per year times 10, is going to tell me how much money extra I'm going to have to spend in 10 years. And if I add that onto my baseline value of 12,000, it's telling me that tuition in 10 years in the year 2020 is going to be $17,989 per semester. That's ridiculous. In 10 years from my baseline year, the year that I just arbitrarily picked, that's what it's going to be. Now, unfortunately, my little girl's 5 years old right now. She is not going to college in 2020. I need to know what's tuition going to be in the year 2030, so 20 years from our baseline. And it's the same idea. In 20 years, it's going up by $552 per year times 20 years, and then I add that onto the baseline, and when I run the computations, it is a whopping $23,000 per semester. Ridiculous. But if this graph is accurate, and if the rate of change stays consistent, and that's an important big if, then that's a fairly accurate estimate of what tuition might be. I can be fairly confident that that's not too far off. Again, an important matter here is that the rate of change is consistent, and that's something that's going to come up with all of the equations in this section, is that when you have a linear equation, the rate of change, that slope is always the same. The general formula that I'm using here, by the way, you might have noticed, is to figure out the tuition cost in some number of years. I take that rate of change, I multiply it by the number of years, and then I add my baseline. This general format, my tuition cost, my output, my y, or my dependent variable, equals the slope, or the rate of change, times x, my input, plus some baseline. This type of equation is called a slope-intercept equation, and that is the main topic for this particular week. So to summarize the information that you're going to see, this is always going to be of the format y equals my slope, which you typically will see the letter m represent that, times x, plus my starting point, which will be called b, is the slope-intercept equation. Let's get into a little bit more detail about the slope in that other letter b. First of all, the slope right here is always going to be the coefficient of x. It's the number that's touching x in this slope-intercept equation. It's talking about the rate of change of x, how fast this graph is increasing when you go from right to left. And often it's called the rise over run, and it's for historical reasons represented using the letter m. The other number here, this guy that's on his own, is called the intercept, technically the y-intercept. And that's the number that's not touching x in the equation. It's always going to be whatever is not touching x. It's the number on its own. It's your starting point for the graph, and we'll talk more about that in a later video, and it's typically going to be represented by the letter b. So to summarize this week's assignments, week 9, we're going to be dealing with this slope-intercept equation. You're going to be looking at the slope, which is the coefficient of x in the formula, and the intercept, which is the number on its own. In later videos, we're going to talk about using a formula to find the slope and using a process to find the y-intercept so that you can put all these things together and construct an equation.